Okay, I'm going to get back to section 12.2 now. We're talking about logarithmic functions, and in the previous video I had defined the logarithmic function to the base a. Okay, y equal log base a of x means x equal a to the y. This is an if and only if, so I could read this statement beginning to end or end to beginning. Both are true, right? So I could also say x equal a to the y means y equal log base a of x. That's what we mean by if and only if. We did some calculations using the definition of a logarithm, and I had mentioned that the definition of a logarithm is, to me, the most important thing to know about logarithms. Like, if you don't know the definition, that's going to be a problem for doing lots of things with logarithms. Okay, so we're on problem 10. And let's take a look at that now. We're going to consider the functions f of x equal 2 to the x and then g of x equal log base 2 of x. Complete the table below and then use these points to sketch the graphs of f and g. We're also going to draw the line y equal x to illustrate that the graph of an inverse is a reflection across this line. Okay, we talked about inverse functions in section 11.6. Okay, and I had mentioned that the topic of inverses would come up again. Okay, and here's where we see that. So let's take a look at this problem here. I've already got a table set up for us. Now I'm going to begin by graphing y equal 2 to the x. Now we have already done that in the previous section. Okay, in 12.1, if you were to flip back in your notes, you'd find that graph already there. That's okay. I'm going to have us regraph y equal 2 to the x because it's going to play a role in how we get the graph of y equal log base 2 of x. Now, when I graph y equal 2 to the x, that's an exponential, and the domain of any exponential is all real numbers. Okay, so like I could let x be anything I want here, positive, negative, 0, doesn't matter. Okay, I'm just using the same numbers that I was using, previously in the last section there. So like if x is negative 3, 2 to the negative third power is the same as 1 over 2 cubed, or 1/8. Okay, so here would be negative 3, 1/8 on the graph. If x is negative 2, 2 to the negative second power is 1 over 2 squared, or 1/4. Okay, so here's negative 2, 1/4 on the graph. If x is negative 1, 2 to the negative first is 1/2. Here's negative 1, 1/2 on the graph. If x is 0, anything to the 0 power is 1, so this curve is going to cross the y-axis at 0, 1. If x is 1, 2 to the first is 2. Here's 1, 2 on the graph. If x is 2, 2 squared is 4. Here's 2, 4 on the graph. And then if x is 3, 2 cubed is 8. Here's 3, 8 on the graph. Okay, and I can draw this curve then. We're in quadrant 2. We're above the x-axis, and we're rising gently. We're going to cross through these points that are already there, and then after we cross the y-axis, we're going to shoot upward and outward into quadrant 1. Remember that a feature of an exponential is that there will always be a horizontal asymptote on the graph. Okay, so while the curve heads outward towards the left, it will never get to the x-axis because you will never have 0 coming out of this calculation, okay, since x is in the power. All right, so we have been there and done that before. This is already in your notes. Here it is again. All right. Now, the very first thing that I had said in this section here is that an exponential function is a one-to-one function. What does that mean again? Well, it means that the inverse is a function. Okay, inverse is all about switching x and y. So if I want to calculate the inverse of y equal 2 to the x, I just switch x and y. All right, well that means I'll have x equal 2 to the y. X equals 2 to the y means y equals log base 2 of x. Okay, that's by definition of a logarithmic function. So that's what I've written over here. X equal 2 to the y means that y equal log base 2 of x. So now I want to graph y equal log base 2 of x. In order to graph y equal log base 2 of x, I'm going to have to graph the inverse function of y equal 2 to the x. Okay, now there I go saying the word inverse again. Inverse is all about switching x and y. So with these points here that I've got from this table, all I'm going to do is I'm going to switch x and y, and I'm going to plot the new points. Let me do that now. Negative 3 1/8 is now going to be at 1/8 negative 3. That's right here. Negative 2 1/4 will now be at 1/4 negative 2. Negative 1 1/2 will be at 1/2 negative 1. 0 1 will be at 1 0. 1 2 is going to be at 2 1. 2 4 is going to be at 4 2. And 3 8 is going to be at 8 3. Okay, so like I said, I'm just switching the coordinates there to plot these new points. And then I'll draw the curve. Okay, the curve is going to be starting off on the right side of the y-axis here in quadrant 4. It's going to be rising and pulling away from that slightly, passing through these points that I've already got plotted. We'll cross the x-axis there at 1 0, and then after we cross at that spot, we're going to curl upward and outward towards the right into quadrant 1. Okay, now all these points on the exponential got flipped, and the horizontal asymptote that was on the exponential is now going to turn into a vertical asymptote on our new graph. Okay, now the new graph is the graph of y equal log base 2 of x. Y equal log base 2 of x is the inverse function of y equal 2 to the x. Now, one of the things that we had learned about in section 11.6 when we were talking about inverse functions is that a function and its inverse are always symmetric about the diagonal line y equal x. Okay, so I've drawn that line, y equal x, and I did that on purpose because I want to illustrate that really, in order to get the graph of this logarithm, I started off with the graph of the exponential and I just rotate that about that diagonal line. Okay, if I do that, all the points are going to land in the spot that you see here where I get this logarithmic curve. Okay. Now, at this point, I would like us to see some major connections with the things that we've learned in the past 2 sections. Okay. Number one, the topic of inverses is essential to studying logarithms. Logarithms is not a topic that you just jump right into. Okay, like there's some preliminary information that you want to make sure that you're fine with. In this problem, like we see that f of x equal 2 to the x and g of x equal log base 2 of x are inverses of each other. Okay, in general, the functions f of x equal a to the x and g of x equal log base a of x are inverses of each other. So you have to know what an inverse is in order to talk about logarithms. Also, you have to know what an exponential is, right? To graph a logarithmic function, you have to first graph the exponential function, like we did here, and then you got to switch all the coordinates, and then you'll get the graph of the logarithmic curve. Okay, and so that kind of summarizes what I'm doing here to get this curve. So like, and that's how I want to handle any logarithmic curve. You know, like if I want to graph y equal log base 5 of x. I'm going to have to first know the graph of y equal 5 to the x, because y equal 5 to the x is the inverse of y equal log base 5 of x. Once I have the graph of y equal 5 to the x, I then switch all the points, and I plot the new points there, and I get the logarithmic curve. Okay. So why we care about logarithms, of course, there's applications and stuff that we'll see later, but the big reason is because a logarithm is the inverse of an exponential. So if you know something about an exponential, you'll know something about its corresponding inverse, which is a logarithm, and vice versa. If you know something about a logarithm, you'll know something about its inverse, which is the exponential. Okay. So there's this inverse relationship going on between the 2 functions there. Okay. Here's another definition. If the base of a logarithmic function is the number e, then we call it the natural logarithmic function. For notation, we write the ln of x to mean log base e of x. You'll see that in all math books. The natural logarithm is defined by y equals log base e of x, or y equal the ln of x, means the same thing. if and only if x equal e to the y. Okay, nothing new here, right? What I just got done reading is just the definition of a logarithm, right? The definition of a logarithm is something that I've mentioned a couple times now. That is the most important thing to know when it comes to logarithms, okay? And so a is the base, okay? And I've just simply rewritten that now using a base of e, okay? So e is a special number, okay? And whenever we have base e, we are working with a special logarithm that's called the natural logarithm. Problem 11. Let's take a look at the graphs of y equal e to the x and y equal the ln of x. I'm going to complete the table below, and then I'm also going to draw the line y equal x to illustrate that these two are inverses of each other. So let's do that now. We have already graphed y equal e to the x in the last section. Okay, if you were to flip back in your notes, you'd see that. And so I'm going to have us regraph that curve because it's going to play a role in how I get the graph of y equal the ln of x. Now I'm graphing y equal e to the x, as I said, which is an exponential, and the domain of any exponential is all real numbers. Okay, so like I can let x be anything I want here in this table. I'm just using the same numbers that we had used previously, when we did this in the last section. So when x is equal to -2, if I type in e to the -2nd power, okay, that's 0.14 if you go nearest 2 digits. Okay, e to the -1st power is 0.37 if you go nearest 2 digits. Okay, anything that's 0 power is 1. Okay, so here's 0, 1. If x is 1, e to the first is e. Okay, or e is roughly 2.72 if you go nearest 2 digits on that. Here's 1 e. If x is 2, e squared would be 7.39 if you were to check that in the calculator. Now that's off the scale that I've selected, okay, but that point would be about right here. There. And at this point, the output values are going to be getting very large. So this curve is starting off in quadrant 2. It's above the x-axis, rising slightly, passing through these points that I've already plotted from my table. It's going to pass through the y-axis at 0, 1, and then after we cross at that spot, we're going to shoot upward and outward towards the right into quadrant 1. Again, I will have a horizontal asymptote on the graph of y equal e to the x. Since x is in the power, I will never have 0 or a negative coming out of the calculation. Okay, so yeah, we have already been there and done that with graphing this curve y equal e to the x. Again, that was in the last section. So here it is again. Now, again, I go back to what I had first mentioned in this section. Any exponential is a one-to-one function. Okay, so it has an inverse, right? Inverse is all about switching x and y. So if I calculate the inverse of y equal e to the x, I just switch x and y. I'm going to have x equal e to the y. Now x equal e to the y means y equals the ln of x, right? That's by definition. So if I want to graph y equal the ln of x, I would need to graph the inverse function of y equal e to the x. Okay, inverse, again, it's all about switching x and y. So with these points here, I'm just going to switch the coordinates and then plot the new points. Let me do that now. Here's -2.14. That's now going to be at 0.14 and -2. It should be right here. Here's -1.37. That's now going to be at 0.37, -1, right here. 0, 1 would be at 1, 0. 1e would be at e1, right here, etc. Okay, so you're just switching the coordinates and then plotting the new points. This horizontal asymptote that was on the graph of the exponential is now going to become a vertical asymptote on the graph of the logarithm. And by the way, that's a feature of a logarithmic curve. There will always be a vertical asymptote on the graph. So this curve is going to be to the right of that boundary. It's going to be pulling away from that slightly. It'll cross the x-axis at 1, 0, and then curl upward and outward towards the right. Okay. Now I've also graphed the line y equal x to show you that y equal e to the x and y equal the ln of x are inverses of each other. Okay, and so they're symmetric to this diagonal line here. Now, in the last section, I had made the comment in the notes saying that y equal e to the x is the most common exponential function. What I meant by that is that there is significantly more mathematical formulas and calculations that you're going to be doing that involve base e than any other base. Okay, so you're going to be working with base e more than like base 2, more than base 3, more than base 5, more than any other base e will come up. Well, with that said, y equal the ln of x is the most common logarithm. Okay, and what I mean by that is there's significantly more mathematical formulas and calculations that you're going to be doing that involve the natural logarithm than compared to any other base. Okay, more than base 2, more than base 3, more than base 5. You'll see base e showing up more than any other base. Okay, we'll stop the video here.